Hello, am I audible? Hello, can any one of the attendees just confirm if I'm audible or not? Okay.
Yes, sir. Audible, sir.
Yeah, thank you, Rakesh. Sorry for the delay. Actually, there has been some technical glitch, so I was trying to resolve that. Give me 1 second. Okay, so I welcome you all to the first session of the NPTEL live, online sessions. So, as you all know, like this was a pilot project of NPTEL to engage the PMRF scholars across all the IITs and the CFTIs into this program. So, I am just a PhD scholar at IIT Madras, and I will be the TA for this particular course. Uh, so, this course is under the tutelage of Professor Shona Kumar Chaudhary. He is from IIT Kanpur. He's a retired professor. So, expecting you all to have at least gone through the videos of the first week. So, yeah, with that expectation, I will be giving my presentation today. And yeah, so I am expecting this session to be a bit more interactive. So, I would like you all to participate in the interaction. And yeah, you can approach with any of your doubts, and I will try my best to solve them in the subsequent sessions. So yeah, then that's it. Okay, so moving on, I have collected a few questions from the week 0 assignment only. So for the first introductory class today, I will be just discussing those basic questions. If you are having any other questions or any doubts pertaining to the content from week 1, then please come up with that. Okay. Rakesh, Prajakta, Hari, Harasudhan, Sakir, Chandrasekhar. I think I'm clear and audible. So, yeah, shall we start now? Uh, any yes or no from your side, please? Okay, thank you. So, yeah, what you can do is you can unmute since the number of participants is less. So, you can unmute yourselves and you can tell me your answer for any particular question. Or if you have any other additional questions to that, we can also discuss that. So, 1 second. Just give me a second, okay? So anyway, like what is the answer for this question in pig iron when we reduce the percentage of carbon, silicon, manganese, phosphorus, this type of elements? Then what is the answer? Okay, so Rakesh is saying it's steel. Yeah, that is right. So just going to the background a little bit. So can anybody unmute yourself and tell like how is the entire process line of this steel industry? Like from where does it start and how do we obtain the end product for this particular industry? Anyone? Just I want to hear the basics only. From what material do we start and how do we achieve the end product in any steel industry? Yeah, hello. I'm expecting an answer from you all. So see, like basically, in Earth we are having the iron ore. Like we are we are not having pure iron as an element available around us. So we are extracting that iron from iron ore. So that's basically iron oxide. So we are reducing it to iron using a blast furnace. So the first product that we are getting after this reduction reactions is pig iron, but it is not suitable for usage in different industries because of poor properties, high brittleness, and all. So what we are doing is we are treating it with different processing routes and trying to make either cast iron or that is like one route, or we are um, making it undergo a different treatment sequence and we are obtaining steel. And subsequently, like during that process, if we are putting in some other alloying elements and all, then we are getting some other forms of steel, the alloy steels, uh, high strength steels. So yeah, low carbon, high carbon steels. So Rakesh, can you tell me like a few classifications of steel? Like steel can be classified into different categories. So can you just name a few of them? I think you have commented something 6.67% carbon. Yeah, that's the percentage of carbon as high as that in pig iron. So with 6.67 percentage carbon, that iron will be so much brittle that it can't be used in any engineering applications. Uh, yeah, Rakesh, hello. Yeah, can you please unmute yourself so that this session doesn't seem to be this much boring actually. Yeah, hyper-eutectoid and hypo-eutectoid steel. I would appreciate if you just unmute yourselves and answer. Okay, so that will be more interesting to me as well as to you, so that other session turns out to be a bit interactive one. Okay, so if you hover through the other options for this particular question, just for some additional informations, say, can anybody tell me what is a composite material? How is it different from an alloy? Yeah, Tawqir, Parvez, Chandrasekhar, Rakesh. Yeah, can you just differentiate between composite material and an alloy? Like how what is the difference, basic difference between them? So okay, so a composite material, it is uh, heterogeneous. You can call it a heterogeneous combination of multiple phases or which are mechanically or metallurgically combined to form one particular element. So element as in one particular material. So you can have, if you have gone through the video lectures, you must have come across different types of composites like fiber composites, particulate composites, or you know, this planar composites where multiple layers of materials are placed at different orientations to form one particular solid material. Like you have this thing, mm, plywoods, which are pasted at different angles. Angles, as in the orientation of the grains, are in different directions. So if you are piling up the layers in such a way that the directions of these grains are in multiple axes, then ultimately you get a material which is having properties, enhanced properties rather, compared to the ingredients properties. So if you are taking one particular layer, suppose it is exhibiting enhanced strength in x direction. So suppose you have laminate. So we call this laminate composite. So if you have a laminate that is exhibiting enhanced strength in say x direction, but it is not having that much strength in y direction or z direction. So what you do, you take one laminate, and the second laminate you place it at an orthogonal orientation, like both of them are 90 degrees to each other. So yeah, Tokir, are you trying to say something? Hello? Yeah, Tokir, can you be a bit louder? Okay. Anyway, so coming back to it, so suppose you are placing the laminates in such a way that its grain orientation is like in one laminate the grain orientation is say in x direction, in the second one it is along the y direction. So if you're piling up multiple laminates like that, so ultimately the final material will exhibit enhanced properties in both x and y directions. So this is the basic model of a laminate composite that I am telling. Like this, you can place the laminates in different other orientations, say in 45-degree angles. So like this, you can make different types of composites. Then if you have then you have particulate composites. Say we have a matrix and matrix material, and in that matrix we are putting particles of hard material. So the matrix is generally soft and tough. So like the final properties of the composite, say we need a tough material, but it should have high strength also. In that case, we need to do some sort of bargain, right? Because if we are taking very high strength materials, it is generally it's inherently brittle, but we can't afford that. We want ductility also, toughness also. So in that case, what we do, we take a ductile matrix material, and in that we put these brittle but high strength phases. They are suspended in this matrix. So together we get a material which is heterogeneous. Suppose this matrix and this particulates, they are not chemically combined with each other. They are not forming any compounds. So no chemical bonds are in between them. It's just metallurgical bond or mechanical bond. So that's the difference. Okay, so yeah. So do you have any other questions from here? So the third type of composite that I was discussing is fiber composite. Okay, so depending on the strengthening material, we can like classify composites like this. So another way of classifying it is on the basis of the matrix that we are using. Suppose the matrix material is a metal, then we are calling it a metal matrix composite. If it's a polymer, then we call it a polymer matrix composite. And if it's ceramic, then we call it a ceramic matrix composite. And like if we want to go into the nomenclature of a particular matrix, like how we are naming them, how we are designating them. Suppose you have a fiber matrix where the fiber is made up of glass fibers and the matrix is made up of polymer. So it is a very usual example. Like in tires, you can see you have nylon fibers or steel wires, and on top of that you have rubber, right? So in that case, the generic name would be glass fiber. If it's a glass fiber, then we will call it a glass fiber reinforced polymer matrix composite. Similarly, if we have, say, silicon carbide particles which act as reinforcements suspended in a cobalt, a cobalt matrix, like the matrix material is cobalt, it is a metal. So we can call it as like I said silicon carbide, right? So silicon carbide particle reinforced cobalt matrix composite, like that we can name it. So yeah, that's it. Then moving on to the next question. Okay, I see a few new faces here. So I'm sorry I didn't admit you because it was not showing up here. So hello Om Prakash, and some other guy also joined. So just to keep you updated, we were just discussing a few basics of like what type of engineering materials we are using. So this was the first question that we discussed, and then we were discussing a little bit about different types of composite materials and how we are naming them. So moving on to the next question, compounds of metallic and non-metallic elements are called. What will be the answer? You can unmute yourself and participate in this discussion. You don't have to actually type it down in the chat box. Yeah, anyone? We just discussed it right now. Like, what will be the answer to this question? Compounds of metallic and non-metallic elements are called. So it's actually ceramic, as it's already written down here. So ceramic materials are basically, combinations of metallic and non-metallic elements which chemically react with each other and form a bond between them. Chemical bond should be there. Then only we can call it a compound, right? So it can be like you have an option as carbide, right? So you might be confused that carbide is also a compound of metallic and non-metallic elements. Technically, it is also a correct answer, but it is just a small class. Like it's a subset of the actual ceramic class, right? So the correct answer would be ceramics. So it can be carbide, it can be nitride, it can be uh, any other phases also, like alumina. Alumina is Al2O3, like oxides, and TiO2. It's also it can also be classified as a ceramic. So there are some inherent properties of this particular ceramics because of which they have become so much popular. So like they have they are brittle. That's a downside of that, but they are really hard. They are very strong in compression. They can sustain high compressive loads, but they're weak in shearing and tension because they are brittle, and they can like withstand corrosive environments. Like if you are keeping it in corrosive environments, they will not really undergo any damage over long periods of time. So that's why you can see that in chemistry labs we are using glass or borosilicate glass apparatus, and sometimes we're using ceramics also. So that's the thing. Then in many cases we are putting this carbide and oxide coatings on metals, so that protects the uh, you know actual metal from corrosive and erosive environments. So these are the properties of ceramics that have made them more popular. Even in cutting tools and different machining operations, we are using these ceramic tools. They can also withstand high levels of temperatures, sometimes well over than 1000 degrees Celsius, which is actually very high. Composite materials, as I already discussed, it is not a compound. It is a you're making them by mechanically or metallurgically bonding two heterogeneous phases to form a heterogeneous like product. And in alloy steels also, like we are putting some alloying elements inside the steel matrix. So it may not be actually chemically bonded with iron or the other elements that is present within it. It can also be suspended as particles or different phases. So we can't really say that it is a compound. So ceramic is the correct answer. During machining of metal, the chip produced is very hot, primarily due to which of the following phenomena? Yeah, Om Prakash, I have seen that you have unmuted yourself. Thanks for that, because nobody is actually doing it, and I'm feeling it a little bit boring. Yeah, Om Prakash, go ahead. Hello, am I audible? Hello. Okay, so yeah, what will be the correct answer? You can type in the chat box also. You're saying maybe because of friction. So, what are the sources of this heat energy during a machining operation? When you are machining a metal, what are the reasons because of which heat can be generated and the temperature of the chip, workpiece, or the tool can go up? What are the primary? I'm not talking about primary, but what are the sources of heat? Yeah, plastic deformation, severe plastic deformation occurs. So if you go a little bit deep down into the machining kinetics or dynamics, then you will find that the like how when if you see how it is occurring. So the metal is coming, suppose in this direction. This is the cutting direction I'm telling, and the tool is placed like this. So the chip is flowing like this. This is the basic geometry that we know, right? So what happens is at the interface of the tool tip and the point of engagement at where it is happening on the metal, it is it is deforming the metal. It is plunging into the metal, and it is severing it from its bulk, right? Like the first layer of the metal, it is getting sheared up, and then it is separated. So during that shearing, you are imparting the energy in the form of Fc into V, right? Cutting force into the velocity at which this is coming and impacting the tool. So that is the power that you are providing, and part of it is being used to shear this particular workpiece, right? And this energy is getting into the material, or the workpiece material, in the form of strain energy. So where will this strain energy go? It is getting dissipated in the form of heat. So that is the primary, reason for the temperature of the chip tool interface to shoot up to very high values. So here you can see the word primary, right? So that's the reason the correct option here is plastic deformation and not friction. Friction is the secondary cause of that heat. When the chip is moving over the rake surface of the tool, then due to some metallurgical and chemical interaction, and as well as the physical interaction, this friction is getting generated. There are some local weldings, that is weldments, that is happening between the chip surface and the rake surface of the tool, and due to these local weldments and also due to the attritions that is forming, the friction force is coming into picture. And due to this friction also, some heat energy is getting dissipated, but that is the secondary. Okay, next question. While drilling, the diameter of the drilled hole always becomes more than the diameter of the drill, due to which of the following options? The tapering in the drill, thermal softening of the workpiece, drill vibration, and vibration of the workpiece. So what is this? How do you actually quantify this particular defect? I will say defect because suppose you want a diameter of 10 mm. Yeah, that is the correct answer, Rakesh. Drill vibration. But now, like technically, how do you define this particular phenomena? Suppose you want a a hole with a diameter of 10 mm, you drill it with a drill bit which is having a diameter of 10 mm. But when you are measuring it in your metrological setup, you're seeing that the diameter now is actually 11 mm, or it can be 10.8, 10.5 mm. So this difference, what do we actually call this? Anyone? What is the term? This is a this property or this mismatch in the diameters. It can be found in any type of machining. If you go in conventional machining or non-conventional machining, and particularly if you're focusing on drilling, then this is a challenge. Suppose you want a hole of 10 mm, but and your operation, like your application is very stringent, like it is having very stringent needs, that I want a diameter of 10 mm only with very less tolerance. So if it is more than say 0.04 mm, which is quite large value, 40 micrometer, which is quite large value, I would say, then that will be discarded. But in actual, you are seeing that it is quite more than what you actually want. So this particular measurement, or it is being quantified as radial overcut. Suppose you want a radius of say 5 mm, but you got a radius of 5.3 mm. So that 0.3 mm can be termed as the overcut. Like you didn't want to cut it, but it got cut. Radial overcut. You can also call it as diametral overcut. Twice into that, that is diametral overcut. So yeah, vibration is a very, you can't avoid it. It will be there in the machine system. So in manufacturing industry, this vibration, it is causing a huge loss, because you have to take care of it and you have to monitor it. Nowadays, like using artificial intelligence and machine learning, many researchers are working on this, that they are trying to monitor the vibration which is actually occurring during this drilling and or other any machining processes. Due to the detrimental effects of this vibration, they are trying to control it. So how that algorithm works is, suppose this is my drill bit, and during rotation it is vibrating like this. I'm exaggerating it. Actually, this amplitude can be in micrometers. I'm just exaggerating it. So due to the vibration, the whole size that you are actually expecting, it is getting enlarged. Okay. So what you are doing is, first strategy would be to choose a diameter, like drill diameter, which is less than the hole diameter that you want. So after choosing that, you have to monitor the wobbling motion of the drill diameter. So using different capturing mechanisms, image capturing mechanisms, and different image processing algorithms, you can actually quantify that how much it is wobbling. This amplitude you can quantify through image processing, and after that you are giving a reverse compensation. So suppose my tool is getting deflected in this direction at any particular instant of time, so you are giving a compensatory motion to it in the opposite direction, so that the tool becomes straight actually. So in that manner, like I am putting one, say, actuator, piezo actuator, or some other types of actuator, which is pulling the drill bit in the opposite direction, and trying to compensate for that deflection. So in that manner, this wobbling action can be reduced to a much larger extent. If you have any question, you can stop me in between and ask. Since today is just an introductory class, we are just dis okay, thermal softening, Rakesh. Like when you are increasing the temperature of any body, it's what happens if you go into the atomic level, the atoms start separating out. The force that was acting, interatomic force, that reduces, right? So that's why the strength of the material reduces. So the force that is actually required to separate those two atoms, it is getting reduced at higher temperatures, and that is why, if you are thinking it now in a bulk, macroscopic way, then when you are putting stress on the metal, you don't have to put a larger value of stress to deform it. So that's why what happens during machining, since the temperature is reaching very high values at the chip tool interface, there uh, the material is getting softened locally, not the entire bulk of the metal, just near the tip. That small volume of the metal near that is getting softened, and that is actually helping you in the process. Like less cutting forces will be involved in such cases. So just you drew attention to this particular option. Thank you for that. I will tell you about another new strategy of machining. Like it has already been patented, but you must have heard about diamond turning, right? Yeah. Have you heard about diamond turning, where you are using diamond as a cutting tool to machine very hard to cut materials, hard to machine materials? So what they are doing, they are putting this laser beam through this diamond. Diamond is transparent, so from an annular chamber, they are passing laser light, and that laser light is being focused at the chip tool interface, that point where the machining is happening. And due to that laser, the you are heating up the material, and it is getting softened. Due to this thermal softening, now the forces that are required, that will be less. Rakesh, am I clear? So that's thermal softening, and that is like not related to this particular phenomena of heat energy. It is actually the material is taking up that particular heat, and it is changing its properties. So it is not related to the heating up of the chip as such. Okay, thank you, Rakesh. Are you acquainted with ECM and EDM? Anyone? Electrochemical machining and electro discharge machining. Vikas. Yeah, I'm not asking the answer, Rakesh. I'm just asking if you're acquainted with ECM and EDM, this processes. See, the main motto of these discussions, live sessions, is not telling you the correct answers to this question. They will already be available after 1 week of your submission of the assignment, right? So the main motto is to have an interactive session. If you are having some doubts, I will solve them. If I don't know, then I will just go and do some research and come up with the solution. So it's a both way learning process, right? That's why I'm requesting you, please unmute yourselves and try to participate in this discussion. That way I will also be able to improve myself. Yeah, anyone. What is ECM? What is EDM? What is the mechanism of this type of, I mean, mechanism means working mechanism. Anyone? So as the name suggests, first of all, both ECM and EDM are non-conventional machining. So there are a few points regarding this non-conventional machining which you will come across in the subsequent lecture series. Yeah, Chandrasekhar. Okay, like I'm not coming to the answer to this particular question. I'm just asking you about the processes in general. What? Okay, just tell me the basic difference between ECM and EDM. Just the basic difference. Just from the name only, you can make out what is the difference between these two particular processes. So, from the name electrochemical, it means that you're using electricity as well as some chemical means to remove the material, right? So here what we are doing, with the aid of electricity and with the aid of chemical reaction, we are trying to remove some material. We are applying electrical energy. That electrical energy is enhancing some, yeah. In EDM, we have spark, Rakesh. So in ECM, we are applying electrical energy. That electrical energy is, um, you know, it is leading to some chemical reactions in the reaction cell, electrochemical cell rather. And due to these chemical reactions, a particular type of chemical reactions, I would say. So in that manner, you're choosing the electrolyte, you're choosing the values of voltage and all. So due to that particular chemical reaction, the anode is getting, like material is getting removed from the anode. So the unique point about this particular material removal mechanism is the material removal takes place atom by atom. Like one atomic layer is getting dissolved, and another atomic layer. Like your, that's why the finish that you are getting is very high, very good finish you are getting after machining, after electrochemical machining. And in case of EDM, what happens? There also you're providing the energy in the form of electrical energy, but at the machining end, what happens? Sparks are coming. Okay, so that electrical energy is provided in the form of pulse. Okay, pulses. So in those particular pulses, these sparks are happening. So in between the tool, first of all, the tool and the workpiece material is not in touch with each other. So that is the first USP of non-conventional machining. In conventional machining, like drilling, milling, and all, your tool and the workpiece will be in constant contact with each other throughout the machining process. In case of non-conventional machining, there is no direct contact between tool and the workpiece. So your requirement of the tool to be harder than the workpiece is eliminated. But still, in ECM and EDM, there is some requirements like your tool and the workpiece both has to be conductive in nature, electrically conductive in nature. That's the basic requirement. And EDM, what happens is, you are like you would say that you're generating some spark in between the tool and the workpiece by providing the electrical energy in pulses, not continuous. Continuous provision of this voltage signal won't give you sparks. It may give you an arc, a continuous column of ionized column of liquid of any particular medium is called a plasma. So if it is continuous over the scale of time, 1 second, then you call it then you call it an arc. But if it is coming in time, in small particular pulses, like t on time, t off time will be there. You will be reading that later. Then in those small pulses, you are having high amount of energy to directly vaporize the material from the workpiece in that small region, small micro volume or macro volume, you can say. Generally, it occurs in micro volumes in microidiom. So in that small part of material on the surface is getting directly vaporized. Okay, so that is the like basic working mechanism of these two particular processes. Then coming to the question, softer tool material is used for ECM in comparison to EDM because in ECM the tool does not wear out. What, Rakesh? Tool wear ratio? Yes, yes. Tool wear ratio is fine. Infine. What is that? Infinite. Tool wear ratio is infinite. It's not actually infinite. It's very high. Like it's high in the sense. First of all, for others, if you're not acquainted with this term, tool wear ratio. So in EDM, I said that spark is happening, and due to that spark, due to that energy, the material is getting evaporated. But it is getting vaporized from, not evaporated, vaporized. So it is getting vaporized from both the workpiece surface as well as the tool surface, right? So you can't eliminate the possibility that that material will be removed only from the work surface and not from the tool surface, right? That you can't eliminate. That will happen. But to reduce that, you are using a harder tool which is having higher resistance to erosion. You're using that type of material as your workpiece in case of EDM. So that's why, like in EDM, you are using a harder workpiece, so softer tool, harder tool material. So that is the reason. Like in ECM, there is no tool wear occurring. In ECM, your anode is the workpiece material, and the material is getting removed by the means of some chemical reaction in atomistic manner, and some ions or atoms are getting deposited on your cathode, right? Cathode is your tool material. To prevent that deposition, you are choosing your electrolyte in such a way that that deposition is not happening. Rather, the atoms are reacting with the electrolyte elements and precipitating in the form in different phases, precipitating in the form of some oxides or some other salts like that. Okay, so in ECM the tool does not wear out. That is one correct option. Lesser heat is produced in ECM, but that doesn't actually justify your need for a softer tool material in ECM compared to EDM, right? Tool is not in touch with the work material in ECM, so that is also the case in EDM. It is physically not in touch with electroplating. Is just the opposite of ECM. In ECM, your object of interest is placed at the anode, because at the anode oxidation is happening. Say I'm taking titanium as a workpiece. I want to machine it. Machine means remove material. That is simple, right? So this is my cathode. So this is my anode. So this is my workpiece. I am bringing my cathode like this, and some chemical reaction is happening in localized in this region, and some hole is forming. Say so, by ECM, I am generating a hole in this titanium plate. Okay. So the anodic reactions, we are calling it as oxidation reactions. So there, the metal ions are coming out from the workpiece surface into the electrolyte, recombining or reacting with other species like oxygen or hydroxides, and either getting deposited here on the workpiece material or getting precipitated. But the one thing is common, that the material is coming out from in like titanium atoms are giving up electrons and coming out in the form of titanium ions into the electrolyte medium. Okay, so that's why the material is getting removed atomistically. In electroplating, your main focus is the cathode, right? Because you know in the cathode, reduction reaction is happening and something is getting deposited on it. So you choose your electrolyte in such a way that that precipitation is not like prominent there. Rather, whatever element is coming out from your anode, that is reacting with the electrolyte elements, and it is forming a layer on the cathode. Okay, so that is electroplating. Am I clear, Om Prakash? That's the basic difference. In ECM, your workpiece is kept at anode and material is getting removed from there. In electroplating, your workpiece material is cathode and material is getting deposited onto it. Am I clear, Om Prakash, or any other clarification is needed? Okay, thank you. So third option is tool is not in touch with the work material in ECM. So that is the same case for EDM also. So that is not the correct answer. Material removal rate in ECM can be enhanced that way. No, like in case of ECM, for to answer this particular type of question, suppose if it was not a single option correct type question, suppose it was a multi-option correct type MCQ, in that scenario you had to go through each of the options before ticking, right? It can be one option correct or two options correct or multiple options correct. So for that you need to know about the basics of ECM and EDM process. Material removal rate in ECM can be enhanced that way. No, you can't enhance material removal rate by choosing a softer tool material. So it doesn't correlate with the strength. This mechanism is not correlating with the strength of the cathode, right, during ECM. It should be more conductive, and also it shouldn't be susceptible to deposition. Like material shouldn't get deposited on the cathode material or the tool. In that case, what happens? Your reaction kinetics will get disrupted, and the features that you are expecting that will not be of good quality. The thermal energy is applied to a very small portion of the workpiece to remove material in ultrasonic machining, EDM, ECM, abrasive jet machining. We just discussed, right? So what is the correct option to this question? Thermal energy. Yeah, electro-discharge machining. So what happens in ultrasonic machining? What is the mode of energy that you are supplying? No, it's not sound. It's mechanical energy. It's not sound. Sound is a wave. Like it's a wave in the air or any particular medium. So the molecules are just vibrating in both x-axis and y-axis, and it is propagating. So that is sound. But in case of ultrasonic machining, you have a tool and you vibrate the tool using a transducer and some piezoelectric actuator or piezomagnetic actuator. So using the transducer, you are that propagation is happening through a horn. You are using a horn. Horn is basically a truncated conical shaped body. So suppose on the top of the cone, you are applying a higher, you know, lower amplitude you're applying at the top, so you are getting a higher amplitude at the bottom of the cone. So at the bottom of the cone you're putting your tool. So what happens? This is the workpiece, this is the tool, and in between the tool and the workpiece you pass a slurry of abrasives. So what happens? It can be a polymeric medium, it can be a viscoelastic or viscoplastic medium, whereby in a particular polymer or in a particular liquid you are mixing some abrasive particles. Generally it's not a polymer, it's a liquid only. I'm sorry. In ultrasonic machining, you are passing this slurry which is laden with abrasive particles. Yeah, brittle fracture, it can be ductile fracture also, but generally it's a brittle fracture in case of ultrasonic machining. So those things we will these minute things we will come across in subsequent weeks, where we will be discussing these things in detail. Today is just an overview. So suppose you have the tool which is fixed at the bottom of the horn, and the tool should be of the negative replica of whatever feature you want on the workpiece. Same in case of EDM and ECM also. The tool should have the negative replica. Suppose you want a hemispherical profile on the workpiece, hemispherical depression on the workpiece. So your tool should be a hemispherical projection. Okay, like this, a hemispherical projection, like my pen, it is having a hemispherical projection. So if the tool is of that manner, then the profile that you're getting on the workpiece is hemispherical depression. So you can say that the tool is having the negative replica of the profile that we want. Same in case of ultrasonic machining also, just the energy that we are imparting, it is different. Here we are providing mechanical energy, so it is vibrating. I'm exaggerating the amplitude, it's much less than this at a high frequency, and we are pushing the abrasive slurry between the tool and the workpiece. Remember that the tool and the workpiece is not in contact with each other. If we in our labs, we generally doing this micro manufacturing. So we have done micro ultrasonic machining, micro EDM, and micro ECM also. So we have observed one thing. This is a very fragile tool. So as you are we are using brittle material as the tool for this. Sorry, we are. I'm extremely sorry. We are machining brittle materials using ultrasonic machining. So as soon as you're bringing the tool in contact with the workpiece, it will break there away. So you have to ensure that it is not coming in contact with the tool. Rather, it is maintaining a small gap, and in between that gap, you are passing the abrasive slurry. So material removal is occurring due to the abrasives getting impinged on the workpiece surface. So the mechanical energy of the tool is getting transmitted to the abrasives. The abrasives are impinging on the workpiece surface, and it is removing material, as Rakesh or Om Prakash pointed out, in the form of brittle fracture. So like that, it is happening. Okay, and abrasive jet machining, anyone knows what is abrasive jet machining? There we are passing the abrasives in the form of a jet. Yeah, sand blasting is not abrasive jet machining. Sand blasting is you're blasting the sand on the surface. So the projection area on the area of projection, it is much higher in case of sand blasting. In case of abrasive jet machining, you are generally focused on one particular jet, so that is impinged on the workpiece. So that jet is carrying the abrasive particles. Abrasives are generally very hard and high strength materials, which it is having higher strength than the workpiece material, obviously. Suppose silicon carbide, then alumina, Al2O3, and diamond dust. We are using them as abrasives. So if your carrier medium, that the jet is, see, when you're pushing the abrasives, it is not coming out of vacuum, right? It should have a carrier medium to coalesce these materials into one particular column. So that's why, like if the carrier gas is air or any particular gas, say carbon dioxide, generally we choose gases which are not reactive, nitrogen. In that cases, argon is also used sometimes. So in that cases, we call it as abrasive jet machining. If we are using water or any other fluid as a carrier medium, then we are calling it as abrasive water jet machining. So in that case, the water is carrying the abrasive particles. It is also enhancing the material removal rate. It is also giving better finish because water acts as a lubricant. So the abrasives, as they are passing, they're like removing the material in a more systematic way, in a more controlled way. In case of abrasive jet machining, some particles are getting reflected, as it is impinging on the surface. Some are getting like in the transverse direction they are moving. So the lubrication is not present. Compared to conventional machine tool, numerical control gives a significant effect on which of the following parameters: downtime, in-process time, both downtime and in-process time, neither downtime nor in-process time. Yes. What is downtime, Rakesh? How do you define downtime, and how do you define in process time? Basically, downtime is the time in which, yeah, idle time in which the machine is not working. The machine, it necessarily need not be the case that the machine has stopped working, or it is under repairment, or it is damaged. It may not be that, but it is not working. Like in that period of time, suppose you are loading your material, or you're unloading your workpiece, or you're simply the material handling operation is going on, or tool changing operation is going on. So you only think, if you are suppose you are acting as an engineer in particular production industry, you have the machines installed, say a lathe machine is there, a milling machine is there. So you need, for a particular product, it may not be as simple as a cylinder. It can have different profiles, different intricate shapes, for which you need different types of operations. It may not be a simple turning. You may have to do a groove, you may have to do some knurling operation, or you may have to do some tapering operation. So for all those cases, in case of lathe machine only, I am telling, you are having uh, multiple scenarios, and multiple tools will be required. In each case, a knurling tool is different from a simple turning tool, or a parting tool, or a grooving tool. It's different. It is having different tool geometries. So if you are an operator, or you are supervising an operator, you will see that he has to change it after every operation. Suppose you have done a few passes of turning, you have got a good surface. Now you want to do this groove you want to do. In that case, you have to change the tool manually. It's a tedious task. Every time you have to put the tool in the correct orientation and load it on um, the stool post and all. But if somehow you are not automating it, you are putting it into some numeric control, like it is happening on its own by some mechanical means, then somehow you are reducing the labor time. Like the person who is doing it manually, that from that it is getting reduced. So during that particular time, your machine is not working, so you can call it as a downtime or idle time. So it is obvious that if you are using a CNC or NC, your downtime is getting reduced. In process time is the time which is involved during the machining operation. So that is like, I won't say that is getting reduced to a significant extent, because your speed, feed, and depth of cut will be same for a particular profile that you want. If you are doing it on a manual lathe machine or in a CNC lathe machine, unless you are going for some high-end strategies like high-speed machining and all, this in-process time will be almost same. So you have the significant term mentioned there in the question. Okay, the next question is, the degree of repeatability in the measurement process is called accuracy, convergence, precision, experimental error. Which is the correct option? Yeah, anyone? Yeah, precision, right. So what is the difference between accuracy and precision? It is it's much sought after question in metrology, right? If you are experiencing this, not experiencing, rather, if you are facing these vivas in different metrology labs, or you will be having lab classes, right, in your BTech. Please elaborate, Rakesh. No, Chandrasekhar, precision is the correct answer. But what is the difference between accuracy and precision? By the way, I just forgot to have this uh, formal introduction. So you all are like pursuing your BTech, or any, like, some other courses are also, you're also involved some in some other courses. Hello, am I audible? Hello? Can anyone please confirm if I am audible or not? This is the problem of online sessions, right? Okay, thank you. So, yeah, all of you are from BTech, right? Yes, no, anything, any answer? No answer. Okay, Rakesh, you have completed BTech, so I'm assuming that you are preparing for GATE, right? GATE exam. Or are you associated with any industry or some company? Okay, okay. So if you are having any doubts, so you can also come up with those questions, GATE questions, so we can discuss them also. Okay, Tokir is telling he's doing a polytechnic, so it's a diploma, right? So you are like you want to convert to BTech, or like you're appearing for these exams, competitive exams. Okay, okay. I'm asking this because then my next I completed my BTech studying cyber security. Om Prakash. Okay, that's nice. Okay, so I'm asking this because I will be designing the questions in such a manner then. Like if most of you are more oriented towards competitive exam preparation, then like my questions will be oriented in that manner only. This is just the introductory class, so I took all the questions from the assignment of week 0. Okay, okay, I will share. But for formal communications or like that, I will just share my mail ID here in case you're having any doubt. And I think you're also aware of this platform on NPTEL, where you, if you're putting your doubts, we will address them also. Okay, so coming back to the question, can anyone differentiate between these two terms, accuracy and precision? I'll be happy if anyone just unmute himself and tell. See, language is no barrier. If you want to say in Hindi, मुझे भी थोड़ा थोड़ा हिंदी आता है. Actually, I'm from Bengal, West Bengal, so yeah, I know Hindi. If you want to, yes, Rakesh.
So repeatability, it is for multiple components maintaining same accuracy for multiple components for a group or batch like that, and accuracy for any uh, particular dimension, etc. For that we maintaining accuracy or for one component. Is
Yeah,
this
see,
right?
like, yeah, you're partially correct. I would say, like, rather than component, if you say measurement, that is more like accurate term, I would say. So the precision is like the same measurement if you're taking multiple times, then it is giving you, say, for the first measurement, it is giving you some value. For the second measurement, it is for the same dimension. I'm telling for the same dimension, same workpiece. Until multiple times, if you're taking, it is giving the same value or similar values. Then you can say it is a precise measurement. But accuracy is like if you are, as you said, like multiple components you are having, and you are taking the same dimension over the multiple components, then if they are close to each other, then you will say that it is more accurate. Your measurement is more accurate.
Okay, sir.
So yeah, if suppose you want you want a diameter of say 10 mm, I said. So at multiple, so this is your hole. You are measuring at different angles. Okay, this is your hole, say, or just consider this pen. Okay, this pen is having a certain diameter. You're measuring at it at different locations. here, here, here at different angles. If you are getting similar values, then you can tell that yes, my measurement is accurate. But suppose at this particular section, this only at a particular section, at a particular angle, you are taking the measurement multiple times. So one time you took, after some time you take, then you can tell that it is precise if you're getting similar values. So it depends on the this precision and accuracy. It depends on the setup, metrological setup also. Suppose you're taking the measurements in an environment where the parameters are changing the measurement values. So in that case, you can't say that my measurements are precise. So this is about the measurement. Now, if you're talking about the component side, then what you said is a more suitable answer to it. One second. I don't know why this thing is happening. Like my screen is blacking out every time. I have to stop sharing and again start. Yeah, so for components, if you are telling, okay, I want to measure the, say a particular dimension, then the same component, if you are measuring multiple times, then if you're getting similar values, you can tell that, yes, it is a precise measurement for this particular component. Accuracy is if you want a particular dimension, say 10 mm, then every time if you are measuring, if it is giving close to 10 mm value, that you are for every component, then you can tell that yes, this has come out to be a more accurate measurement.
Yes.
Even for the same component, you can say like for that 10 mm only, you are measuring multiple times. So how close is your thing is coming? Like how close is your measured value to 10 mm? That gives you accuracy.
So this, what is this convergence?
Convergence means is like your data is converging to a particular value. Like it generally in case of errors we are bringing in these terms. So what we want is the error should converge. Like it shouldn't diverge. Like I'm giving you an example. Say suppose you have to take some sequential measurements of a particular object. Okay, suppose you take one x measurement in x direction, then using that measurement and then you take a measurement in y direction. Like that you're taking multiple measurements. Okay, so in each measurement some error will be associated with it. So finally, if you are calculating, say, the volume, the volume will be including each of these measurements. Like it can be volume, it can be some other parameters also, which comprises of which is a function of all these particular measurements. So if there will be errors in each measurement, right? So it shouldn't be the case that all these errors are it is augmenting to give a larger error in the volume. So, like, I'm not sure if I'm able to answer your question or not. So, it is,
That means that should be minimized.
yeah, the convergence is like the error should come down at every sequence of the measurement. So, that's why, like, what I will do, like, now I am not having any material to explain this numerically. In the next class, I will try to give a numerical example. Then that will be more clear. Okay. Without data, it's difficult to say that
Okay,
how
sir.
the error converges, how the error diverges. Yeah. But if you have come across this course on numerical methods, one course is there. So if you have gone through this course, then you should be acquainted with this term, this convergence, divergence, all these things.
Yes, sir.
Okay.
Yes, sir.
Hmm. I think okay. This is the third last question. Cross feed in turning process is used to get a flat surface, make a groove, make a cylindrical surface, make a formed surface, make a null surface. So what is cross feed? I think you're acquainted with it, right? So feed is along the length of the workpiece, that is along the longitudinal direction during turning, and cross feed is feed perpendicular to the direction of longitudinal feed. that is into the bulk of the workpiece. So this, suppose this is my tool, okay, this small metal piece you are seeing, this is my tool, this is my workpiece, it is turning. So this direction is cross feed, and this longitudinal direction along the length of my pen, that is longitudinal feed, okay, during turning operation. So in which of these following operations do you need cross feed? So it is a combination based question, like 1, 2, 3. Which of the following combinations are correct? C maybe. Not sure. P is telling 1, 2, 4. Get a flat surface. Yeah, that is correct. Like see, I'm taking this bottle. Okay, it is easier to visualize. Suppose this is the workpiece. It is rotating at certain RPM, and this is my tool. Say this pen is now my tool. This pen. So if you want a flat surface, this focus on this particular surface. If you want to get a flat surface here, then you give this infeed in this direction. Okay. Infeed or cross feed, whatever. So for that you have a tool with this side cutting angle as 90 degree. That side cutting angle should be 90 degree. That type of tool you are needing. Then to make a groove, yeah. So this is my workpiece. So here, if I want to make a groove, then also I need to put the move the tool in this particular perpendicular direction. So in that cross feed only, with that cross feed only, I will get this groove. So 1 and 2 is correct, and 5 you're telling making a nulled surface. Nulled surface is like you won't get a null surface using cross feed. Null surface, for that you are having a ratchet like particular type of tool called knurling tool. So when you are placing it against the workpiece and rotating, that that type of profile is getting replicated over your workpiece, over the entire periphery. So what are the other points? Making a cylindrical surface. No, for cylindrical surface you have to give longitudinal feed. Making a formed surface, yeah, for making a formed surface you need the formed surface is basically it is having some type of form. Say this is a fairly, you can assume it to be a truncated cone. Okay, this particular portion, it is conical in nature. So to get this type of profile, which we call as a formed profile, formed surface, we need to give feed both in longitudinal direction as well as in perpendicular, that is cross feed direction. Only then we will get this type of profile. If you are giving feed only in this direction, you will get a cylindrical profile. So you have to give a profile in this direction also, right? Then you will get this type of taper. So this is just a simple example of formed surface. It can be in the form of some complex forms may be there. So the correct answer here is 1, 2, and 4. So D is the correct answer. A machining operation where the tool reciprocates and the workpiece is given an incremental feed perpendicular to the movement of the tool. That is a very simple question. But there is one catch here. Like, what is the answer? Anyone? Yeah, shaping. What is the difference between shaping and planning? Drilling, milling, turning can be conveniently ruled out. But what is the difference? workpiece size, that is the requirement. What is the like technical difference between these two machining operations? For handling larger workpieces, what you are doing, like what different are you doing in planning? In shaping, you can say, okay, my workpiece is small, we are doing something. In shaping my workpiece is in shaping my workpiece is small, I'm doing some type of this for generics and directics, I'm following some type of kinematics and dynamics. In case of planning, I'm following some different type of kinematics. So what is the difference? See, in shaping operation, your workpiece is fixed. Okay, sorry, not the workpiece is not fixed. Your like tool it is moving in the along the cutting direction, and the feed, horizontal feed, is given on the workpiece. The tool is just reciprocating, and the workpiece is moving in the feeding direction, perpendicular to the cutting direction. Okay, but in case of planning, as someone pointed out rightly, that we are handling larger workpieces. So in that case, it is like rather than traveling the tool over a long span, which is you must be knowing how this reciprocating action is happening, right? If you have come across this mechanism, can you name the mechanism which is adopted? No, no, milling. See, milling is not the right answer, right? Like, no, 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 not ratchet and pinion. See, there is no mechanism like ratchet and pinion, I think. It's rack and pinion and ratchet and pawl. These two are different things. But in case of shaping machine, we are using one type of mechanism. So you take this as an assignment. Yeah, right. Slotted lever, not crankshaft. It's a slotted lever, but there's more technical term to it. Some you can take this as an assignment. Just remind me in the next class. We can discuss a little bit about it if time permits. So if you, in case of planning, your workpiece size is huge. If you want to incorporate that slotted lever mechanism to make such long distances of to and fro motion, yes, right, quick return mechanism. It is a quick return mechanism. So quick return mechanism, it can be adopted by using different types of mechanism. Like if you're using slider crank mechanism also, if that the line of motion of the reciprocator, if it is and offset from the axis of rotation of the crank, then also you will get a quick return mechanism. Okay. Suppose this is the crank, so the center of the crank, it is not in line with the reciprocator, it is offset with the reciprocator. So here it is reciprocating, and here is the center. So there is some offset distance. In that case also you will get a quick return mechanism. Uh, okay, so like in case of planning, what happens? You have a large bed, large workpiece. So if you have to incorporate such a long motion of the tool, then you have to make a huge slotted lever mechanism or whatever, quick return mechanism, which is not economical. Rather than that, you put an XY stage, you move the workpiece in the XY direction with the help of the stage. Hello? Yeah, can anyone confirm if I'm audible or not?
Audible, sir. Audible. Audible.
Okay, okay. One second.
Sir, what is intermittent feed and what is its use?
Sorry, Rakesh, can you tell me again? Can you ask the question again? Hello? I didn't get you. Can you put the question again? Like, what is the difference between? I didn't get the two terms. Okay, intermittent feed and what is the other term? Continuous feed, right? Okay, I'm assuming it is continuous feed that you're. Yeah, right. Okay, so see, in case of turning, what happens is this is my workpiece. Say, so this feed motion you can see on the top. Okay, this I'm showing. This is my tool. This is the workpiece, and the view you are getting on the camera. It is the front. It is the top view of the motion. Okay, not the front view. It is the top view of the machining operation. So this is my workpiece. So I am. This is my tool. I am. The workpiece is rotating, and I am giving the feed in this direction, and it is continuous feed. I am not bringing out the workpiece and again putting the feed. Oh, sorry, I'm not bringing out the tool and again giving the feed. Again bringing out the tool, giving the feed. That I am not doing. I am touching the workpiece continuously and like at a given depth of cut, I am giving the longitudinal feed. Okay, but in case of incremental feed, as in case of shaping operation, so this is the feed I have kept in intermittent feed, not incremental. I'm extremely sorry. It's intermittent feed. So this is my shaping tool. So once it has gone like one complete path, like it has completed one forward and backward motion, then I am giving the next, feed motion, and and after that I am not giving any feed motion. At that time again this cutting motion is happening, then I am giving the feed motion. So this feed motion is not continuous, it is intermittent. In between the cutting operations I am like giving this feed motions, and that is intermittent in nature. So that is the difference between intermittent feed and continuous feed. Am I clear? Okay. Okay, so that was the last question for today. If you have any doubts, please ask. You can ask in Hindi if you want. Okay. Welcome, Om Prakash. In case you are not having any questions, shall we wind up the session for today? Vikas, Rakesh, Chandrasekhar. If you have any doubts, please come up. Design questions in such a way that it will help in exam preparation. Okay. From the next class onwards, I will give some numeric. I will add some numerical questions which will be helpful for these competitive exams. And this type of questions also can be expected in many competitive exams, like in prelims sort of exams where you are checked the basics. Like you are expected to, have good grasp on the basics. There you can expect this type of questions. It may not be directly from here, but some twisted concepts can be built from the basic questions. Okay, thank you. So we will meet again next Friday at 7 p.m. I will try to join a couple of minutes earlier, unlike today. So, yeah, thank you for attending. And if you're having any doubt, you can post it directly on that NPTEL portal, on that platform. There's one, um, you know, place for entering your doubts. So they will be addressed adequately. So, yeah, and please go through the videos for week 1 and week 2 for the next class. This was just an introductory session, so I didn't discuss much about material properties, flip systems, and all. In the next class, you can expect some questions, some conceptual questions from those topics as well. Okay, and do solve the assignments. I think 2 assignments have been rolled out for week 1, so solve them within time. Okay, thank you. Bye.